Hi guys. There seems to be some magical sweet spot between running at PowerPoint and click. So apparently that works. I want to make a use of that and just go on. This please again don't see that again. Yes. It gives you the various imaging techniques in biomedical tools, broadly speaking. So, you have confocal microscopy, focus tomography. On the top you have spectroscopy, CT and MRI. Also the ones later with megahertz ultrasound techniques. You can see that by some coincidental way, they make up this range of trade-offs between the depth at which you can look and the resolution at which you can image. So basically, what you can find here is that if you want to image something that's a little depth, you don't really care about how deep you can look. This range, for microscopy or OCT, if you really need to image all organs, then your method of choice would be PET. Of course, water is not the only one. It's not the only absorber in tissue. There's a lot more. The most important ones are hemoglobin. Yeah, exactly. Yeah. So that's really important. And then the either oxygenated or deoxygenated regarding on how many molecules it finds. There is of course hemoglobin breakdown products such as bilirubin, fatty short life can be important. For example, if you would like to quantify constituents of black components, for example, melanin, and then various components. So if you then look at the absorption spectrum, so again on the vertical axis, the absorption coefficient, wavelengths, nanometers, you can see how these different components, these different tissue constituents absorb light. That of course means also that if you want to design a technique, or if you want to design a measurement that measures some property of blood, for example, this would be to limit your measurement length if you would like to do something that is the water content. Well, limit measurement. So it seems that when I'm talking too long, then perhaps it's a bit. Yeah. Yeah, that's good as well. Yeah. So the thing that I'm an engineer by trade. Yeah. This is really embarrassing. Je hebt er maar één bij mij, dat doe ik al. Kan me niet. Ik was gewoon verbaasd als kijken dat het maar enkel was, maar. I'm just going to speed up things a little bit. So, are you familiar with the velocity diagram? Anybody who is not familiar with the velocity diagram? Yes, I think. So it is kind of a schematic to show energy levels within molecules. And you can actually use it pretty nicely to describe how light works from light to the tissue. So if you look here at this basic diagram, we have a ground state here with a thick line. There is some excited state levels from that ground state with the thin lines over there. First, if light interacts with such a molecule, it can excite the molecule up to any of these excites. From that, a number of processes can occur. You could have a non-radiated transfer, for example, just fall back from some excited states to some ground state level, then back to another ground state level, and back to maybe even to the ground state. In that case, there would be no energy transformed. All the energy would be transformed into heat. Right. So that would be one basic reflection, heating of tissue. Heating of tissue can be a very important application. Cut tissue, treat tissue, weld tissue. What we would like to do is just have as much as possible energy from the light being turned into heat and those burning of tissue. Of course, you can this is scary. Of course, you can do a lot that tell you how the temperature, the change, the rate temperature with time changes with position and time function properties tissues. Top of there, spatial dependency on the temperature gradient. And there is also the absorption. That's the point I want to make, of course. Because the absorption coefficient is basically our measure of how light, how effectively energy of light is transferred into heat. So typically what you would have to solve equations like this in order to calculate the response. Of course, in many situations, many applications, it can be a little bit simpler. Just to give you an idea, just give you a ballpark number of what the values are. Proteins start to be measured at temperatures that are 100 heat of fission even further to 60 degrees or more than the existing fluid. Yeah, of course, because so as you can see from that hidden this equation, that the absorption coefficient is spatially dependent. So how much light we apply at some position. So you could use, for example, you could use a beam that is really, you could take a laser. You really focus it into a very narrow spot, which means that you would basically deliver all the energy there, and most of the energy would there be converted into heat. Or you could have a much broader illumination profile. A lot of tissue. Yeah, so heat is one of the most straightforward principles. This is interesting. This is an imaging technique that's actually based on the generation of heat. What you can do here is that you can excite tissue, so you can put in some kind of laser pulse that delivers heat, that delivers energy to the tissue, which is transferred to heat. That heat, which is expansion, ultrasonic expansion, which you can then again detect with an ultrasonic detector. And so that means that again the most likely absorber in tissue is going to be either water or gas. Specifically, have that water or blood heat up, expand a little bit, generate an instrument signal, and detect that. And then, for example, in this case for blood, you can measure, you can map the vascular structure. You can do this, for example, around tumors. So tumors are really really strange tissue. The way that they are very tumors are very invasive. They want to grow. They do not care too much about having a proper vascular structure. The normal tissue would have a proper vascular structure that would support giving food and energy to it. But that's not so much the case. So measuring, just visualizing the vascular structure of tumors, very telling, very diagnostically indicative for how bad the tumor is. Really aggressive tumor, it really does not care about this, and a very sloppy way of just because of heat, so it's a rapid heating. So the laser pulse is very intense. So it will just energy has to go somewhere that goes into expansion. So it rapidly heats up and then it relaxes again. And that heat up or relaxation that causes the and then basically what the graph shows is actually true. So it goes, it's not just directed one way, it's actually directed two ways. So you can have multiple detectors, you can have multiple locations. Then we can start back how the yeah, another probably very familiar mechanism is so here we have that excitation light excites the molecule until some excited state. There is a non-radiated relaxation to a lower incident. And then after that, there is a gradient. So that means again, photon is emitted. So you put in light, you get out. So again, if you look at the equation that related energy to the frequency, so what happens here is that because you have a large energy step going up, there is a non-radiated relaxation to here and radiated to here. So this energy step is less than the excitation energy step. Energy will be less, this means that the wavelength will be higher. So you will get a photon out, you will get light out. Formally you could call it that because you have no idea which direction it goes. And especially since the lifetime. With the lifetime, I mean the time it takes for this process to occur. It's in the order of picoseconds. To even to microseconds, so it can be pretty slow. Well, of course, you can do this all these great images, and I'm going to show that great many of them. Because do that, and people do that, and those will do that. So you will see plenty of those points. Of course, the specific expertise of Lutz is a great variant. So I'm not just using one photon to bridge that gap until higher two photons simultaneously short, then the energy is simultaneously transferred. So you can basically get the same effect. And then using two photons without the energy, or say two photons have the wavelength. So again, there is a big bump to some excited state, and there is a little bit of non-radiated relaxation to the lowest excited state, and then there is a decay emitting a photon. But in this case, because we have two photons doing the excitation, it means that the energy of the emitted photon is going to be larger than the photons of the energy of the photons of the dynamics of this process are a little bit different. So here too, the lifetime is about the same ballpark number, probably a little bit lower, and you need much more photons. You need, so you have to have incidental. Basically, it has to be, for instance, You have to have the coincidental absorption of these two photons. And that just does not happen that often. So that means that you have to provide for a lot of photons in order to get that. So you need large functions of power. This one is so now we're getting this is really getting exotic because the Jablonski diagram is now much more complicated. So we instead of just having three energy levels, we also have spin multiplicity here, so singlet states, and you can have energy crossing between these levels. So it can get more complicated. You could have an interaction with light that excites to let's say F2 and then some excited state of that non-radiative relaxation to that ground state, and then some energy crossing up into some neutral state. From there, you can fall back to the ground state. Well, you don't have so again, the relation between the excited photons and the emitted photons are just determined by the energy. Again, more energy for excitation, less energy for emission. It also takes longer because these triplet states tend to be more stable. So that the phosphorescence lifetime, so the whole time, the process take place can be as much as milliseconds to hours. You get probably soon. And again, no matter how exotic the process is, we can use it for either trying to do some kind of imaging or trying to do some kind of therapy. So this is an example that we use that for. So on the left-hand side, you see the Jablonski diagram of a metallic polymer, a molecule like hemoglobin. With a few different energy states and a few different preferable system crossings where you happen to get so we can use light to excite from S0 to S2, let's say. It will fall back non-radiated one, and then there will be some system crossing, and from that on, we can have basically two effects. We can either have the classic phosphorescence, where the photon is emitted while it falls back to the state, or it can be coupling with yet another molecule. In this case, that would be oxygen. What would happen here is that the phosphorescence, so basically you can go both ways. It can either go back to the ground state to emit the photon, or it could be transferred to the oxygen. So what we can see is a very indirect way of measuring how much oxygen is present in the tissue. There's a lot of oxygen, then in the end you will see high oxygen pressure. You would see a lot of quenching of the present. All that is if there's low amounts of oxygen, then there will be more emissions. So we can actually use that. To measure how much oxygen is present as a reaction. This has been used in the experimental clinic. This is the reaction is really short out. My good friend Berknik published a paper in Nature Economics with very simple setup. Just measuring how fast the phosphorescence will decay, relating that to the mass oxygen. You can also use that for treatment because oxygen is quite it's quite a reactive species. You would be able to excite oxygen from its normal. Oxygen is a little bit special because it has the ground state of oxygen is in the triple state, and then the excited state will be in the single state. Too much detail for now. But if you would be able to transfer enough energy to oxygen, to free oxygen, to get it from the stable triple state to a single oxygen state, it becomes very reactive. It can affect DNA. And as bad as that sounds, if there is a cancerous cell, that's exactly what you want to do. You would want to target that cell in the DNA level. That cell, that cell. So how that then works is given in the cartoon out there. So oxygen is supposed to be there all the time. What does that do? You can administer this metallic poison. Looks like hemoglobin, but okay. So you can inject that into the body. Then by the way that these tumors are organized, care about how good vessels are, it just needs a lot of vessels. That also means that they're very leaky. So whatever that injects in the body will end up in the tumor with some kind of preference. So you can inject it, it will end up at the tumor site. Then at the same time, you can shine light on that exact same site that the tumor is going to be. And then this whole process is going to take place. So selectively damage the tumor. All right. Now the I made it very complicated. One slide has to make things a little bit more simple. So what happens if you do not excite until the energy level? The so-called virtual energy level. So these things are not supposed to happen. So it means that their lifetimes are not very, very short. So it means that whenever you're able to excite until that virtual level, you can immediately go back. That also means that because this level is virtual, the wavelength of photon wavelength light is within the and this basically is another way of looking at spectrum process. So there is no transfer of energy. There could be some change in direction. Basically, that's what's happening there. Last one. Then, more complicated, and most complicated. You can also look at the mass spectrum. So here on the left graph. Yeah. Good question. I don't know directly. No, that's the honest answer. No, the thing is they are not discrete vectors. So they can be anything. But there is no, as far as I understand it, there is no real preference for one or the other. So for scattered, so in terms of this picture for scattered or light, so that really does mean that it does not matter. So let's say you have S0 here, you have S1 somewhere up there, in the friction level over here. If you would match the S1 level, then the light would be absorbed. If you match anything in between, then the light will just be scattered. Maybe a little bit to simplify it. Two important distinctions are to be made here. So if you have the radius scattering, then the energy level of the excitation light and the emitted light will be exactly the same, and it will fall back to the ground state. Two variants from here are that light, so you can excite a molecule to some virtual state and it will fall back not to the ground state, but to some kind of neutron state. That would be called Raman scattering, Stokes Raman scattering. And the other way around, what also happens that it starts off at some kind of excited level, and then excited rotational level gets excited to an immediate state, and then falls back. Of course, with all the considerations about photon energy and photon levels, you can now reason which you have a larger wavelength, so we use the same wavelength. Here is less energy, so we excite with a larger amount of energy than that is different. So what would that mean for wavelength? Here is of course the other way around. Yeah. In this case, yeah, that's a good question, because apparently the molecule was already in some kind of state. So maybe it's some other. There you're asking good. So which of these processes is more likely? Yeah, because it's not really likely that the molecule is going to be here. It's much more likely that yeah, now you're talking about the more exotic processes where yeah,
because they are in the same
generation
of state.
Yeah, so you can these are usually called flow. You can use one wavelength to excite to an intermediate level, then fall back, back, for example, to this level. Then you use another photon with another, and you excite even further to another. It's an endless amount of possibilities. But Johannes will talk about that. Okay, let's take a break there, guys. I want to talk to. So after the break, I want to discuss a very basic, very down to earth way of using this absorption measurements for diagnostics. That is measuring jaundice in units. My chance is going to be to not everyone stop.
Ik had het over wat ze die absorptieeffecten hebben. Ik kan dat absorptie dan maken dat was volgens mij ook die ooit twee dat ik ook ooit waarbij ze dus energie kunnen absorberen. Ja, precies. Maar dan is het natuurlijk dat je een hele hoge dan heeft het wel misschien ook
Zo heeft met maken. Ik weet niet welke energie precies op kan. Maar ik bij die die bepalen waar de energie is. Wat je maakt is dat we vaker nooit dat nooit alleen. Dus het is dus waar je misschien met als je factuur laat zetten, zou je één volteken of één frequentie hebben. Maar je studeert in de praktijk altijd uit omdat je.
Oké, ja.
Het was om na die drie colleges maar hier tussendoor dan ik zal het nog even ja, het is net speciaal als ik het zei. Omdat ik hij gooit van op zich ja, ik word nog wel een beetje zo
Hoe laten we het nou?
een kwartier. Ja, dat is een kwartier.
Maar wel echt.
Nee, ik dacht die had makkelijk open en die dacht. Ja, als we om 3 uur weer naar
Maar wat voor mij ook. Nee, muziek is niet altijd. Soms staat het dus ook al bij. Soms staat er wel bij van de tekening door aan de plastic. Gewoon even controleren voordat je. De enige nee, joh. Ja. Nee, dat kan ik niet. Nou. Nee, met jou durf ik helemaal niks te doen. Hij is cool, hè? Ook natuurlijk. Wat? Ja, dämlich. Je wilde achter.
Nee, dan is het nog goed. Ja, dat is oké.
Nee joh. Join the dark side. Ja, die klopt niet. Dan is
It seems like we're going faster. It's getting really dark. I can put on some lights, but it seems that so let me know what you want. So what I want to work at now, is using these absorption properties of the tissue components to make an actual measurement that is clinically relevant. There's two examples here on the slide. One of them you know sure. Hopefully not witnessed in person, but otherwise you have some detail. The other one is it's a little bit more complex. Checking bilirubin levels. We'll talk about that in a minute. Basically, the three steps that we're doing here, we're trying to do is first measure shine light, detect light that comes out. Then, from that measured signal, we try to extract a absorption coefficient, absorption spectra, if you do it with commercial reference. using some kind of theoretical model for that signal. So we have a model for the signal. Try to fit that, for example, data in terms of that model. Then that would ideally get us to a quantitative measurement of absorption coefficients, and then the next step is to make it really clinically relevant, translate these absorption coefficients into something that is really with physiology. Don't place. So that the doctor can actually do something. So not just measure the absorption coefficient of oxygenated blood, not just measure the absorption coefficient of some bilirubin, but translate that into oxygen saturation. Bilirubin. That will then be the next step. Again, a little bit same kind of caveat I made slide now. We brought it as a wave or as a particle. Same question we can ask ourselves a little bit at to what scale do we look at the properties. Because there's a very small LED illumination vision, you can imagine that there's a number of scales at which you can look at this problem. So, for example, you can look at the vasculature as a whole. That would be a lamp and a larger piece of tissue. If you would zoom in a little bit more, you would get the single red blood cell, for example. Zooming even a little bit further, it could be looking at hemoglobin. So I'm just giving this as a caveat. We have to be really careful at what scale we look at. At some point, we also see that translates a lot of these things. Just to be safe. So let's start at that molecule. Let's start at that symbol. Of course, that already is the microscope, it can be fluorescence microscope already. Raman microscope, it looks differently. So how do we characterize that? That is already different. So just pose this. This is how we illuminate the molecule with certain intensity. Intensity 0. What per square meter? So what is the power? Let's concentrate that. And the molecule has a geometrical section. Let's work with that. So in that case, the incident power. So if the frequency is then the incidence power of a molecule is going to be I0 times G. Because units watts power is what's put from square meter. That would be the incident power. Now let's say that this molecule absorbs light. There is a certain amount of power absorbed, and we call that amount of power dA. Then, with this additional definition, we can define a quantity that describes the efficiency of this molecule to absorb light. Not very surprisingly, it is called surprisingly, it is defined as ratio of the absorbed power over the incident power. Dimension how good efficient absorber This is just reiterating the equations that we have. So this is the equations. Now let's manipulate a little bit further. We can then also give an expression for the absorbed power itself. We can define that as QA times the geometrical cross sections times I0. And it works out I0 has what per square millimeter GF. Square millimeters per square meter. Efficiency was dimensions. So we can now, by manipulating, by rearranging these terms, get an expression from the absorbed power. Because why not group two of these terms together? Why not group QA, the absorption efficiency, geometrical cross section G together into this single quantity? So we can define now, we can now write the absorbed power equal to absorption cross sections times. We're almost there. I'm not going to get you any more exotic. The absorbed power is always going to be less than the instant power. Not much more likely to be absorbed.
It says less or equal. Is that also possible?
Yeah, that's also possible. Although all the light could be absorbed. So that would mean that this absorption cross section defined is going to be less turbulence. So this was looking at a single molecule.
Just fantasizing a little bit about how what the size of a molecule could be, what the incident power could be, what the incident intensity could be, and how you can then relate these things together. But how about now if you look at a bunch of molecules? So let's take not one hemoglobin molecule, but let's take a bunch of them. And then it already starts to make sense to look at an experiment and not so much at. So let's put these molecules in a cuvette. We'll keep the same convention, so we know that for each molecule it will have a absorption cross section sigma A. That absorption cross section is going to be equal to the absorption efficiency Q times the geometrical cross section of that same molecule. But we'll put a bunch of them in a cuvette. That cuvette will be illuminated with intensity I0. There will be some intensity at the back of that cuvette I, which we are trying to measure, and the cuvette can have thickness L. So now let's say that the cuvette is filled with identical molecules. There will be n of them, number n, in a volume V, and that volume V is then given by some area A. So that could be that will be then the illuminated area of that cuvette times the thickness of that cuvette. So I've added a bunch of geometrical constraints now. But so far so good, I guess, right? So then the question is, can we now? We had expressions for the absorbed power by a single molecule that was given by the absorption cross section times the incident intensity. Now the incident intensity that we assume known. The absorption cross section we calculated for that molecule from the geometrical cross section and some kind of magically given Q. But if we now would like to calculate this for all molecules. Can we then also calculate it for all molecules? So what's your guess? That's a good guess. How?
Because we know the incident density, we know that we can measure the density that gets out of it. And with Lambert Beer, we can express the absorb power, I guess.
Yeah, that's one. If you look at it from, can you also look at it from a different perspective? So not from the measurement side, but from okay, what happens if so I have one molecule? Let's say I have one molecule and I know exactly what happens, and now I have 10. So what? Yeah, the sum of so if the concentration is not too high and if the molecules don't get in each other's way, then probably 10 molecules are going to absorb just 10 times as much as one molecule. So that's a very reasonable thing to expect. Yeah, so that's then the first the first thing to write down. So the total absorbed power by these n molecules is going to be just n times the absorbed power by one of the molecules. And there will be a lot of exceptions to this rule. Don't worry, but not now. Alternatively, you could answer. So again, a lot of this is rephrasing the same thing in different ways. What you could also say is that the total cross section of a sample, so not so much of a molecule, but of a bunch of molecules, the total absorption cross section is the sum of the individual cross sections. So n, in this case, just n times the cross section of that molecule. If the molecules are all the same, then it's just a simple product. If the molecules are different, then you could just have to add up all these different cross sections. That could also happen. Okay, let's go on. So this is where we were. We had a cuvette filled with number of n molecules. The volume was V, which was an area A times the thickness L. The molecule number density is the number density is basically the number of molecules per unit volume. So that would be n over V. That would have units per cubic meter, number per cubic meter, and we can give it a symbol rho n molecular. So let's look again at this total absorption coefficient. So the total absorption coefficient of all the molecules in the cuvette all added together. And our idea was that, okay, if they are not interacting, if they are happily going their own way, then we can just add the absorption coefficients, absorption cross sections, I'm sorry, and then we would get the expression over here. Now let's combine that with the expression for rho. We can define again. This is I promise the last new quantity. We can define an absorption coefficient or the density of absorption cross section by taking the total absorption cross section of all the molecules and dividing that by the volume. So that would be a density. Well, you can go about it in two ways. You can look at the equations. You can combine that, and you will see that what you end up is that this density of absorption cross section is a rho. So the number density times the absorption cross section of a single molecule, like this. And you can look at the units, and you will find that it has units per meter per length. And not coincidentally, that was exactly what we had on all these graphs just before the break. So what we did here now is we scaled up. We did not we started out with a single molecule. We started out with the properties of the molecule, and then we made a few simple assumptions. And now all of a sudden we have an expression, we have a measure for a whole bunch of molecules, in the cuvette. So let's go on. So these are the molecules in the cuvette with this number density. Now let's see what actually happens with that light, because we're interested in doing that measurement. So we can just looking at it, what happens is that the light travels straight through from some source to some detector. Some of it is absorbed, that is gone. The rest is not interacting, so that just continues. So what we can do is, in describing this, is just divide this cuvette with length L. So the length L is along the path of the light, into these small steps, these small slices with thickness delta L, so to say. Now then you can calculate the number of molecules in each of these very small slices. So along the way as the light propagates, so that would be delta n would be the density times A times delta L in this case. That would be the number of molecules. And you can still do the same thing. You can still say, okay, if I know this number of molecules, then I know what the total amount of absorbed light is. So that we can write that down. So the absorbed power in such a slice, somewhere in there at L, is then delta PA, is then delta N, the amount of molecules, times sigma, times the absorption cross section. So just combining all the equations before, we can now write an expression for the amount of power. So delta PA in watts as a function of the number density of the particles, rho of m. A was the area, delta L was the length. So together they are volume, and then we have sigma A, the absorption cross section at that position. That's nice and good, but not that interesting as much. So we can also calculate the change of intensity. So if this is the amount of absorbed power in a slice at L, then delta E is delta P divided by A. Again, look at the units. So this is watt per square meter, is watts divided by square meter. Is the change in intensity when you pass through a slice of delta L. And from that, so that is carrying over from the previous slide, and that means so the change in intensity, you can write that as a differential. So the intensity at some position L plus delta L minus the intensity at some position I of L, just at one tiny step before that, is given by the previous expression. So this is all building up to a differential equation, as you can see. So you can write it like this. So the rate of change of delta E with the rate of change of L is given by the expression over there. And then if you solve that differential equation, you get Lambert-Beer's law. This is just basically a very complicated way of arriving at something that Lambert and Beer did already many years ago. So you will find an intensity I of L as you go along the cuvette. That is given by some constant, of course, but whatever you put in, and then an exponential decay that is proportional to the number of particles in the volume, so the whole M, that is proportional to the absorption strength of one of the particles, and that is proportional to the length of the cuvette that you go through. Lambert and Beer were actually a good example of pre-war European cooperation, because Beer was German and Lambert was French, and they both discovered different sides of the equation. So there is some kind of symmetry to that. This is what I wrote. What I would like to do is have you work. So a lot of things here. Can you go on Canvas or not here? Is that? Yeah. Okay. So I've put this part on Canvas as well, so you can just read it as well. Otherwise, ask me. What I would like you to do is just work a little bit with these numbers, work a little bit with these translations. If you have a molecule of a certain size, can you then calculate the absorption cross-section? Can you then calculate the so the topic is bilirubin. That's a breakdown product of hemoglobin. Hemoglobin, you know. It will bind to albumin, which is yet another protein, and it will transport it to the liver, and then it's getting broken down, and then eventually it's excreted just in the normal way. The problem is that children that are preterm, early born, they do not have sufficient enzymes yet. So this whole breakdown cascade cannot work. It's not cleared. And what happens then is that it's really just basically pushed into the skin, because it's a little bit of yellow. It has a little bit of yellow color. These children get this kind of yellow appearance. There's actually two forms of that bilirubin. One is not so bad. The other one can lead to brain damage. So that is not so good. So what usually gets done for the benign variant is that these children get UV illumination. They will just be in a solar bank for a little while, and then it will break down, and nothing is wrong. If the non-benign, the malignant version is present, and then more treatment is needed. There. So, again, talking for too long. Okay, let's see. So apparently this is a natural moment to have a break. So I would actually like you to Ha. So what do we know? What do we know about bilirubin? Well, a couple of things. So the cross-sectional diameter is approximately 1 nanometer. The structure apparently looks like that. We can do measurements of the compound, and we can extract the absorption coefficient. what you see here is the molar absorption coefficient. So it is slightly different than the absorption coefficient that I've presented before. So that was in units per meter or per centimeter or per millimeter. This one is corrected for concentration. So this is per centimeter per molar. But then the value, the maximum absorption value of that would be 450, at a wavelength of 450 nanometer would be 50,000 per centimeter per molar. Then what we also know is that in typical jaundiced neonates, the molecular density is 0.2 millimolar. And that would translate into 10 to the 17th molecules per square centimeter. So we have a lot of numbers. So the questions are, my questions are now for you. So given the written definitions that we had of the absorption efficiency, the absorption cross-section, and the absorption coefficient, and how they're all related to each other. So what were they and what were the units? Question one, just to get started. Then, can you calculate the absorption coefficient, the absorption cross-section, and the absorption efficiency for this bilirubin concentration? And then there's an additional question, but that has to do with practicalities, but let's get back to that later. So how do you want to do this? Because maybe it's already also break time, so we can also say that I'm just going to leave you for 20 minutes or so for a break and work on this. If you're just going to take a break and not work on this, then
I don't know if it's just me, but I think we have many breaks, and for me, I'd rather continue and leave a bit earlier.
okay, yeah, that's good for me. That's good for me as well. Okay. Okay, so then the immediate follow-up question is: do you have enough to work on now with this data and what you can find on Compass?
Do we have to submit this? Or?
No. This is just
exercise.
yeah, to have you actually finally getting to work with. And by all means, if you have any questions, then just come and then ask me. So.